Hello everyone, my name is Lin. I'm now studying for a master degree at Beijing Information Science and Technology University. Today, I'm going to share my paper titled Combining Deep Learning and Expert Rules for Smart Contract Vulnerability Detection. I will present my paper from the following six parts. In the first part, I will introduce the background of the research. In 2016, a security vulnerability in the DOL contract led to the loss of more than 3.6 million Ethereum tokens. In 2017, the parity contract was attacked, resulting in the theft of $30 million worth of Ethereum. Therefore, it is critical to detect contracts for vulnerabilities before they are deployed. According to whether the source code needs to be executed, existing smart contract vulnerability detection methods can be divided into two types, static and dynamic methods. This paper mainly focused on static detection methods. The static methods can automatically scan and analyze the contract code without manual inspection line by line, which reduce labor costs and time consumptions. The static methods can be divided into two categories: vulnerability detection methods based on expert rules and deep learning. Based on expert rules, this method based on expert experience and domain knowledges, which can accurately identify specific types of vulnerabilities. Based on deep learning, this method can learn complex features from data and are able to mine more vulnerability patterns. However, both methods have their own drawbacks. For example, based on expert rules, not effective in detecting new types of vulnerabilities or vulnerabilities not covered by expert rules. Based on deep learning, performance may be limited by insufficient data quality or poor data quality. In the second part, I will discuss the motivation of the research. We use the as order dependence memo and the migrations contract to illustrate the limitation of using single methods for smart contract vulnerability detection. Taking the expert rules based on detection method material as an ample example when checking the as type order dependence manual contract. Material cannot detect the transaction order dependence vulnerability as it doesn't have expert rules specifically for this type of vulnerability. However, when detecting the migrations contract, Masreal successfully detects the deny observe vulnerability because it has predefined rules for the type of deny observe vulnerability. This is also the case with the use of deep learning-based methods contract word to detect these two contracts. So, we propose CDVD, a smart contract vulnerability detection method, combined deep learning and expert rules. In the third part, I will discuss the approach of the research. The ball figure shows the framework the CDVD approach, which consists of two phases: model training and vulnerability detection. In the model training phase, it first extracts smart contract syntax features from the training set. In the feature extraction part, we follow the SOL matrix proposed by Yang et al. For solidity and extract the matrix of smart contract code as features. The picture on the left shows the SCSOL matrix. Then input the training set into the expert rule-based model. Based on the detection results of the expert rule-based model, smart contracts in the training set are labeled as deep learning prone or expert rule prone. Finally, we train the SCDMC with the extracted features and the detection category labels. In CDVD, we use support vector machine as SCDMC. SVM is the supervised learning algorithm for classification and regression analysis. Its fundamental principle involves finding an optimal hyperplane to discuss between different categories of samples. In the vulnerability detection phase, syntax features are first extracted from the samples and the analysis. Then, these features are input into the trained CDMC to select appropriate vulnerability detection methods. In CDVD, we use Mandu and Mesriel as deep learning-based and expert rule-based smart contract detection methods, respectively. Yeah. Mandu is proposed by Nguyen et al. To detect vulnerabilities by learning the structure of heterogeneous contract graphs. Mesriel is a symbolic execution tool developed by Consensus for detecting vulnerabilities in algorithm virtual machine bytecode. In the fourth part, I will discuss the setup of the experiment. The following two research questions are designed to verify the effectiveness of CDVD. First, compared with other smart contract vulnerability detection approaches, how is the performance of CDVD? Second, what is the impact of using different classification models for SCDMC on CDVD performance? The table above shows the details of the dataset we used. The experimental metrics utilized accuracy, precision, recall, and FE score. In the fifth part, I will discuss the result of the experiment. To comprehensively evaluate the overall performance of CDVD, we compare CDVD with Mandu and Mesriel, in which Mandu achieves SOTA performance. Figure 3a to E illustrates the performance of the three methods in detecting 5 different types of vulnerabilities, and Figure F representing the average detection results. We can see CDVD outperformance using single detection method for vulnerability detection. Compared to the SOTA method Mandu, CDVD achieves improvements in 4 metrics for the 5 types of vulnerabilities. For the second question, we use 6 different classifiers as the SCDMC. Compared to other variants, CDVD SVM achieves the best performance in recall and MV score with an average improvement of 3.667% to 8.48% and 0.9 0.92% to 5.85% respectively. We can still state that CDVD SVM doesn't achieve the best results in terms of accuracy and precision. However, it should be noticed that in vulnerability detection scenario, record gets more attention to avoid false negative. Meanwhile, FE score compares both recall and precision metrics, which is also more important. Overall, CDVDSVM is most suitable to be used as CDMC. In the sixth part, I will discuss the conclusion and the future work. In this paper, we propose a smart contract vulnerability detection method combined deep learning and expert rules named CDVD. Meanwhile, we conduct experiments on a dataset containing 536 smart contracts and compared CDVD with baselines. As part of our future work, larger data sets with more types of vulnerability will be used to validate the effectiveness of CDVD. In addition, we plan to extract more discriminative features of smart contracts to predict suitable vulnerability detection method more accurately. Thank you to all teachers and students for listening.